And hello once again, APIP physics students. We've got an exciting problem for you today. We're going to do problem number 40 from chapter number 7. So I hope your interest in physics hasn't decayed by this point. Decayed. Because this problem is about a radioactive decay, which is kind of cool. So in this problem, it states we have a nucleus, right, made up of protons and neutrons discovered by Rutherford, right? And so we've got a nucleus, and it decays. It undergoes a beta decay. And after this beta decay, we have a neutrino that fires out of the nucleus in this direction. Neutrinos are represented by the Greek letter mu, or pardon me, nu. And then there's also an electron that comes out of the nucleus, and the problem states that it comes out at a 90-degree angle from the neutrino. So what I'm drawing in here is a momentum vector. This is the momentum of the neutrino, and this would be the momentum of the electron. And then, of course, since momentum is conserved, the nucleus recoils in this direction. So this would be the momentum of the nucleus. Okay, and the problem gives you what the momentum of the electron is. It states the momentum of the electron is 9.30 times 10 to the minus 23rd kilograms times meters per second. And it also says that the momentum of the neutrino is 5.4. Is this right? 5.4 times 10 to the minus 23rd kilograms times meters per second. Okay, so I kind of have these drawn a little backwards, huh? My electron vector should be a little longer here. So what kind of decay is this, by the way? This is kind of random, a little aside here. This is a beta decay, where a neutron in the nucleus essentially turns into a proton, which stays in the nucleus, an electron, which fires out of the nucleus, and in this case, it would be anti-electron neutrino that fires out. Anyway, that's just, you don't need to know that. That's just kind of fun. Okay, so the question in this problem is, what is the magnitude and direction of the recoiling nucleus? So I've got this nucleus, and the nucleus will have lost a little bit of mass and or energy because of the decay, but the neutrino fires out that way and the electron fires out this way. What's the momentum of the recoiling nucleus, and at what angle would it recoil? All right. Well, so let's take a look at this. So this would be the momentum of the recoiling nucleus. So wouldn't this then be the x component of the recoiling nucleus? And wouldn't this be the y component of the recoiling nucleus? Why did I put that in there? What's happening there? Well, as it turns out, the x component of the recoiling nucleus's momentum would have to be equal to the momentum of the recoiling nucleus. At least they would be equal in magnitude and opposite in direction, right? So at first, the initial momentum of the system is 0, right? So in the end, the net momentum of the system must be 0, meaning the x component of the neutrino's momentum must exactly cancel out the x component of the nucleus's momentum. Okay, so we would know that. Also, we would know that the y component of the nucleus's momentum would have to be equal and opposite to the electron's momentum, right? So this guy here would have to cancel out that guy there. Initial, right? Because if final momentum is 0, then if initial momentum is 0, then final momentum would have to be 0. Since momentum would be conserved, since there's no external forces, momentum would have to be conserved. So we could say that the magnitude of the nucleus's momentum would be equal to the square root of the magnitude of the electron's momentum squared plus the magnitude of the neutrino's momentum squared. Okay, so plugging in our numbers here, we would plug in to square root here of 9.30 times 10 to the minus 23rd squared plus 5.40 times 10 minus 23rd squared. By the way, if you're ever doing a problem like this on the AP test, remember, don't type in that 10 to the minus 23rd and square root. Just know that your answer, just do 9.3 squared plus 5.4 squared and take the square root, and then just know your answer will have a factor of 10 to the minus 23rd in there. So when I did that, I got 10.8, right? And then I would just know that's times 10 to the minus 23rd. So simplifying that, we would get that the overall magnitude of the nucleus's momentum would be 1.08 times 10 to the minus 22nd kilogram meters per second. Okay, so put a little box around that here. All right. So conservation of momentum, even at the atomic level, is in full effect here. So it also wanted to know a direction. So we could solve for a little bit of theta here. Okay, so let's say we put a theta right in there. What would that angle be? Well, theta would be the inverse tangent, right, of the opposite over the adjacent, which would be equal to the, let's see, the p sub y, which was the electron's momentum, right? So that would be 9.3 times 10 to the 23rd divided by 5.4 times 10 to the minus 23rd, and I'm not even going to write in the 10 to the minus 23rd because, you know, they'll just cancel out, right? So theta ends up being, if you type that in your calculator, theta is 59.95 or 60 degrees. Now, if this angle is 60 degrees, what your book said was that if you look up the answer in the back of the book, it says the nucleus's momentum is 150 degrees from the momentum of the electron. Right? Because if this is 60 degrees here, then this angle here would be 60 plus 90, 150 degrees. So that's a nice way of writing it because the angle is not relative to any coordinate system that we've defined. It's just relative to the electron. All right, so another great example of conservation of momentum in 2 dimensions. And a nice little problem because it works on the atomic level and it's kind of neat. All right, for today's joke for hanging in there, AP Physics students, I have something that an old Far Side gallery for you. Oh, Gary Larson, you are so funny and you have such great cartoons, and we are going to zoom in here. Right in on this funny guy, right? Oh my goodness, I zoomed in too much. And look at this funny cartoon. Oh, there goes Williams again, trying to win support for his Little Bang Theory. Because Williams looks kind of little, so he has a Little Bang Theory. Oh, Gary Larson, you know the what makes a physicist laugh. All right, nice job, AP Physics students. We'll see you in class tomorrow. Keep up the good work.